So welcome back everybody to EE240. I think based on the number of people here, this question will have a slightly biased sample set, but how many of you guys are done with homework number 4? Okay, that's what I thought. So nearly 100% of those in attendance are done with homework number 4. So obviously for those of you guys who are somehow watching this, I don't know, live, even though it's not exactly lively casted, obviously that's due later this afternoon, so make sure you get going on that. By the way, I will be handing out sort of the first phase of the real project probably early next week, probably like on Tuesday essentially. We haven't quite gotten to all the material we need to know to really do that first phase of the project, which is why I'm not handing it out right away. But that'll be up. That'll also be due sort of essentially 2 weeks from today. That first phase shouldn't be too bad, so very similar to sort of previous years if you've taken a look. The first couple phases will be sort of more like homeworks, and then the final phase of the project is really where I open it up a lot more and you have freedom to kind of explore the design space and really understand what's going on. So that's just more of a heads up than anything else, nothing you sort of need to worry about right away, just more for planning purposes, keep that in mind. So for those of you guys who are here, any kind of questions on either material so far or homework or anything like that? I guess you guys are done, so less likely to have questions. Yeah?
For the settling time, do you have to show both like the settling when it goes up and when it goes down?
Yeah, well, so if you built a single-ended amplifier, then you certainly should, because remember, the slewing behavior may be different in the two directions. So you should certainly show both of those to make sure that actually the settling you've claimed works in both directions. You know, if I answered a question that you didn't, and you happen to turn your thing in, it's still all in the box. You can grab it back and still make changes if you want in case somebody realized they didn't do something they should have and happens to be here. By the way, one other thing, which there was a question about last time, there was indeed a typo in the homework handout. It said something about, you know, for example, if you quote 150 millivolts, then you should settle to within plus minus 300 microvolts. That should have been 375 microvolts. If you met 300 microvolts, obviously you're fine, so don't worry about it. Okay, any other questions? Or? Okay, so let's maybe dive back into the material. So last time we were talking about common mode feedback, and really where we sort of ended up in some sense was saying how for the same reasons as we wanted to use capacitive feedback for our differential amplifiers, you essentially want to use capacitive feedback for your common mode control as well. And again, really for much of the same reasons relating to not reducing the DC gain or trading off with power consumption. So at the end, we kind of talked about this relatively simple capacitive feedback structure here. And we kind of ended up sort of motivating a little bit just how much gain you'd actually need for that common mode feedback loop, and how that sort of came into the picture in terms of choosing the size of these common mode feedback capacitors. But really kind of the next thing that we need to sort of deal a little bit with here is that because we're using this capacitive feedback, just like in the differential case, if you don't actually initialize these capacitors to some value, you don't really know what's actually happening across there. So you can kind of only say something about the changes in the common mode, but you can't really get the DC part of it right, which of course is the whole point of doing this common mode feedback in the first place. So what I wanted to show was sort of, in some sense, let's say the brute force initialization scheme, which maybe actually in some cases would indeed be what you will use, but just walk through what some of the issues would be in terms of actually putting something like this together. So if you look sort of over here, this is really the same capacitive common feedback amplifier that I had before. But now what I've done is I've just added some switches in here in order to actually initialize the voltages to where I think they're actually quote-unquote supposed to be. Okay, so again, just to be sort of clear, the idea here is that this V bias is just coming from our standard current mirror. Okay, and then this VCM0 right here, that's just somehow, magically, it's the voltage that I know that I want my common mode output to be sitting at. Okay? So maybe not today, but probably next week we'll have a little bit of discussion about just how would you even decide what that voltage should be in the first place. But for now, let's assume that we kind of know roughly what that voltage, let's say we know roughly what we want that voltage to be. Okay? So the way this thing is working is kind of simple, right? So essentially in this phase, which in this particular case would be the phase that we're not necessarily using the amplifier. So essentially while we're sampling the input signal, basically we turn all of these switches on. Okay? So that's kind of just saying that I'm going to feed V bias directly into the gate of that current source device, just like you would normally do when you kind of for example, if you've done in your homework this time. But interestingly, on the output, I'm also going to turn these switches on. I'm just going to directly tie the output to this VCM 0. Okay? So essentially, I've initialized the voltage across this capacitor to be VCM 0 minus V bias, right? But maybe more importantly, I've forced the output of the amplifier to actually sit exactly at VCM 0. Of course, assuming I made my switch resistance small enough and etc. Okay? So the idea here is that in one phase, I force it to sort of sit where it's supposed to be. And then in the next phase, by turning off all these switches, now I know where everything started. And so the normal feedback loop will kick in to try and maintain it in that same nominal condition. Okay? So I can certainly initialize things this way, but anything sort of maybe annoys you or that seems like maybe it's a little bit potentially problematic by doing things this way? What do you guys think? I'll give you a hint. Does anybody really give you magic voltages with 0 output impedance? Probably not, right? So this voltage has to be generated by something, right? So what's going to happen, for example, if you really do have somewhat of a common mode error? So let's say there's a little bit of, I don't know, plus delta I right here. And actually plus delta I right here as well, of course. So if there's a little bit of extra common mode current, when you turn on these switches, where is that extra common mode current going to flow into?
VCM?
Is that current? Well, remember, if I turn these switches on, then I basically am just connecting VCM0 directly to this point right here. So where's that extra current going to flow into?
The voltage source.
Yeah, it's going to flow into the voltage source, right? Because if this was really a voltage source, then there would be 0 impedance here, and all of the current would just flow into that voltage source, right? Now, of course, this isn't really a voltage source. It's actually some circuit that we built. So, of course, it's going to have some output impedance associated with it, okay? So really, there's kind of two problems here. So one is, if there really is a big common mode error, then what you'd have to do is you'd have to make sure that when you built this bias thing over here, that whatever is driving that bias has a low enough output impedance that when you sync that common mode current, it doesn't cause a big disturbance, right? It basically doesn't cause the voltage to go to the wrong place. Now, that's maybe not so bad, but it means that, for example, you know, usually when you do these biasing kinds of things, you don't really want to spend a lot of power on that, right? But if I actually have to dump a bunch of extra common mode current into there, I may actually have to build this as, you know, my normal reference, whatever it is, and then actually put a buffer to drive that thing. Okay, you can do all that. In fact, actually, a lot of times if you look at sort of mixed signal design, half of the time it's about designing all the stuff around your circuit and not the actual circuit you care about. But you don't really want to have to spend power when you don't need to, right? You don't want to have to spend power on building this buffer that may handle bunches of current that, you know, in some senses is not really useful from the standpoint of your circuit. Okay? The other thing is that you can imagine whenever you close those switches, if there was any kind of residual error there, it's going to cause a big jump at the output of the amplifier, right? Because let's say that the output of the amplifier, I don't know, let's say this was like VO plus and this was VO minus, and from whatever reason that common mode was slightly off. So when you turn on those switches, what's going to happen is something like this, right? So it's kind of going to be a big disturbance at that output. So that might actually cause some glitches on the supply. That also, of course, means that you can't actually use this amplifier during that period of time, right? So although this all sort of works, it's maybe a little bit more brute force than we had intended. So what I want to walk through just really quickly is show you another example of how you can actually do a essentially capacitive common mode feedback, but do it in a way that actually doesn't necessarily disturb things quite as badly. And in fact, may even allow you to use the amplifier in a sort of continuous time way. but still do the capacitive feedback. Okay? So, again, there's many different ways you can do this, but this is just going to be sort of one example here. But I'm going to show this example because it's a sort of fairly typical one. So again, this V bias down here, that's really just, again, going to be created by a diode-connected transistor. Okay? But really what I'm doing here is it kind of looks like a fairly small modification, but we'll see in a second it has some interesting characteristics. So really all I've done versus the previous circuit, and by the way, I didn't draw the whole amplifier here just because I'm lazy and it would have made the picture too big, so obviously there's the other half that's symmetric on this side as well. Okay? So what I've done here is I still have this capacitive feedback piece right here. I still have the same switches that I had before to actually connect it to eventually VCM0 and V-bias. But now what I'm going to do is I'm actually going to add another capacitor and another set of switches in between over here. Okay? So let's maybe just sort of walk through what happens in the two different phases here. So by the way, this phi amp and this phi samp doesn't matter so much when you do which one of them. They're just meant to be two non-overlapping clocks. Okay? So let's look at what happens sort of in quote-unquote the first phase, which is when phi amp is on. Okay? So in that phase, the circuit I have looks something like this. So I have VCM0 here, I have V-bias there, I have that connected across that first capacitor, and then of course the second capacitor is just tied up kind of in the nominal way like this. Okay, so that's VI plus, and this is CM. Okay? So that's kind of the first phase. Then in the second phase, in other words, when phi samp turns on, really all I'm going to do is basically connect CCMS to be in parallel with CCM. Okay? And of course the rest of the circuit is tied up sort of the same way as it was before. Okay? So now here's the sort of interesting question for you guys. Let's say that, I'm at the beginning of time right now, and from whatever reason there is somewhat of a common mode error at the output. So as an example, let's say that I know that nominally I want this to be 200 millivolts, meaning I want the difference between VCM0 and V-bias to be 200 millivolts. But from whatever reason, initially over here on CCM, I've only got 100 millivolts of difference. Okay? So, let's say this is, what happens in the beginning. Once I go into this phase and I close or turn on these two switches right here, I put these caps in parallel. What's going to happen? What's going to happen sort of to the voltage across here?
Get divided.
Okay, divided between what and what, I guess?
Two capacitors.
Okay.
Charge sharing. Right?
Ah, there we go. It's going to charge share, right? So basically, I had some amount of charge on here. I had some amount of charge on there. Charge can't go away. So all that's going to happen is the charge is going to redistribute between the two caps to make the voltage equal. So, okay, obviously, without telling you the values of the caps, I don't know what that value of the voltage is going to be. But, what's the range for that voltage, given the numbers that I gave you initially over here?
Between 200 and 100.
Yeah, it's going to have to be somewhere between 100 and 200 millivolts, right? So, certainly, what that basically means is, unless I made, if I made this even some very, very small size, this voltage is going to start going up, right? Which is kind of exactly what we want, right? Because we know that we wanted this voltage to actually be 200 millivolts. And so by connecting that cap in parallel with it, we're going to start boosting it up a little bit, right? So now, what's the advantage of doing this versus, for example, this method over here? Well, if I choose this CCMS to be, let's say, reasonably small in comparison to this CCM, then every time I close the switches like this, I'll just be like moving a little bit of charge around, right? I may be only taking a small step in the voltage at the output. So in other words, if I've sized this up properly, I might even be able to use this in a way that you can't even really tell that the common mode is moving around a little bit, right? In other words, you can make the disturbances reasonably small, okay? Now, by the way, you should sort of notice this will indeed eventually converge to being the right voltage, because obviously there's nothing else really forcing the value across here to be something, right? So eventually it's going to essentially have to go to be whatever this value that you've sampled onto the input actually is. Okay? Yeah.
So if IL has some extra delta I, that is kind of putting charge on CCM, right?
Mm-hmm.
So is there some, has to take more charge off than
Great.
adding? Or?
No, you're absolutely right. So actually, and we're going to talk about this in 1 second, what you're really doing here, what this whole structure right here actually looks like, if you kind of think about it, is a resistor. Okay? So by the way, who's ever heard of a switched capacitor resistor? A couple people. Okay, we're going to talk more about it. Don't worry if you haven't heard about it before. We'll sort of go through all the gory detail. But as you were kind of saying, if there's some extra amount of current over here, you're sort of going to be charging this thing up, right? The only way for you to remove that charge is by essentially sucking some of it onto this capacitor right here, and then shoving it back into these voltages right here, right? So you're absolutely right. You still have to be careful that essentially whatever these excursions are, the output impedance of your common mode control circuit is low enough that you can actually suck that thing off fast enough. And by the way, just in case it isn't clear, you can kind of imagine every time you connect these two together, like in this phase, some of the charge from CCM will show up on CCMS, right? Then in this phase, once you connect it back to the voltage sources, that charge is going to get yanked off, right? Because it's going to be forced back to this nominal voltage. So again, we'll talk some more about switch capacitor resistors, but actually that's how switch capacitors or resistors work. You sort of grab some packet of charge from one place and move it over to the other place. It's just you're doing that periodically over time, so it's not exactly how you normally think about a resistor, but actually the overall function over a period is kind of actually the same thing. Okay? So that's actually a great question. Does this kind of make sense to people, or? Okay, so really from 10,000 feet, the idea here is just essentially how you can do things in a slightly, let's say, more continuous way to sort of smooth those charge packets out. So potentially allow you to actually use the amplifier more continuously. But really kind of the global point of the lecture was indeed to just take a look at some of these different common mode feedback schemes and understand what the issues and trade-offs would be from a design standpoint so that when you go and you build your differential amplifiers, which, don't worry, you'll be doing, you actually know how to build some of these common mode feedback control circuits. Because again, if you ignore that, it's like the classic interview question that gets people stumped. It's the classic, build a circuit and it doesn't actually work when it comes back from the fab. All the stuff that you basically want to avoid. So, any other kind of questions on this stuff, or? Yeah.
So basically, you're just setting the right voltage difference, but over longer periods of time.
You can kind of think of it that way, right? So you can kind of say that that might be similar to doing something like this, but having a reasonably large resistance there, right? So you could actually do something sort of similar in this case. This is just sort of a nice, convenient way of doing it, particularly if you actually are using this whole thing in a sort of, let's say, switch capacitor context, okay? So a lot of times just, you want to build things in this way because, as an example, you can actually control very, very precisely what the time constant of this thing is going to be. And again, we'll see exactly how that works when we talk, and again, maybe one more lecture about sort of switch capacitor resistors and what the effective resistance actually is. It's a good question. Other questions on this? Or? Okay, great. So if not, let's go ahead and actually move on. And let's start actually talking about our next real topic, which is going to be multi-stage amplifiers. Okay? So hopefully it should be somewhat obvious to you guys why we're even talking about this in the first place, because if nothing else, you should have seen a lot of this stuff from EE140. I'm going to focus on some sort of maybe more advanced or slightly different techniques than what you've seen before. Okay, so just first of all, why do we want multi-stage amplifiers at all? Well, as we talked about many, many times in the context of sort of single-stage amplifiers, and let's just sort of draw an example here. So let's say I had my very simple single-stage thing, so this is some V bias, and I have some V in over here, and I have V out right here. Well, in general, if I want to basically trade off between, if I want to get a very large swing, then oftentimes I can't really have too much gain, right? Because as an example, over here, the wider I make the swing over here, the closer I'm going to be pushing one of those two transistors out of quote-unquote saturation, right? So the lower the output impedance is actually going to be. Similarly, if I want to maybe get a higher RO, then I could do something like, let's say, add in a cascode, right? But again, as soon as I do that, I'm giving up some of the swing that I can actually get, right? So bottom line, if you really wanted to do it, or in fact I should say, since you oftentimes really do want both large gain and large swing, what you oftentimes end up having to do is actually build a multi-stage amplifier, okay? And in particular, a two-stage amplifier. Simply because when you do a two-stage amplifier, let's say you take, and I'll just, of course, draw it conceptually. You just take something like this. Your swing is set by, obviously, that second stage. But your gain is the multiplication of the two gains, right? So actually, even if the gain of the second stage is not huge because it has a high swing, the first stage doesn't necessarily need a lot of swing. So you can actually put a lot of gain there, right? So in fact, if you sort of think about it, all the gain-boosted cascode stuff that we talked about is really just a multi-stage amplifier just kind of disguised in a clever way, right? Where you sort of tie that second stage into an internal feedback loop, okay? So pretty clear why we might actually want to use multi-stage amplifiers. But of course, as soon as we do anything other than just, our nice single stage like this, you have this sort of obvious challenge, right? Which is, how are you going to make the darn thing stable? Because now you don't just have one pole, you actually have multiple poles, so we got to worry about the stability in terms of tying this whole thing into a feedback loop, okay? So just to sort of set up the discussion, what I want to do is look at a very, very simple sort of two-stage amplifier. Okay, obviously you're not really going to build things exactly in this way, but it's actually going to give us a good idea of what some of the issues are going to be, okay? So let's say that, again, I just have this very simple sort of silly two-stage amplifier. And just to be clear, let's pretend that there's actually some output resistance R1 on the first stage and some output resistance R2 on the second stage, okay? So first of all, just, let's, doing this very simple thing, where are the poles for this amplifier actually going to be? So where is the first pole actually going to be?
1 over R1 C1.
There we go, just minus 1 over R1 C1. Of course, the second pole is just going to be minus 1 over R2 C2. Okay, so let's say that, I made these things reasonably similar to each other. So let's say P1 and P2 are kind of somewhat quote-unquote close to each other, and I'll quantify what I mean by that in a second. Now, here's my sort of question. So given that I have these two poles and they're sort of closely spaced with each other, is this circuit stable?
Open loop.
Okay, well obviously if it's open loop then I'm not doing too much. So let's say I do close it into some sort of feedback. So again, is the circuit stable? Say that again?
Probably not.
Probably not. Okay, well, so by the way, this does actually happen to be a trick question. So what do you need to know in order to answer my question as to whether or not it's stable?
What's the closed loop gain?
Yeah, I kind of need to know what feedback did I put it into, right? Because obviously if I just ask you a question about stability and I don't say anything about what is this feedback box I'm putting here, then I don't know, maybe it's stable, maybe it's not. Depends, right? Depends on what I've actually put there. Okay? Now there's actually one other sort of, I don't know, maybe side comment or maybe question. So what happens if I told you, okay, fine, this is just some gain. Okay, and by the way, I put the minus sign here because obviously the gain from here to here is positive. And so if I had a positive gain in the feedback, I would just be building an oscillator. Okay, so but let's say I even told you this is just some minus f. Let's even say it's minus 1, let's say. Okay? So I've put it into unity gain negative feedback. And let's say almost, I just choose these poles. I'll even be mean. I'll put them right on top of each other. Okay? Is this circuit unstable? What do you guys think? So I see some people saying, yeah, it's unstable, but so let's maybe remind people. What do when I say stable, what does that actually mean?
Doesn't oscillate.
Doesn't oscillate. Okay, that's kind of. So let's actually go with that definition. So let's say this was really exactly my circuit, meaning the small signal model of just a GM, an R, and a C. Let's say that was really the actual circuit. So, would this oscillate?
Unity gain feedback?
Unity gain feedback.
No.
Okay, why not?
Well, basically by the time you start to have the 180 degree kind of phase shift, you're already pretty far below unity gain. So.
Are you?
Loop gain has to go.
Because remember, I put both of these poles right on top of each other, and I have some sort of gain, right? So I have any gain greater than 1. So actually, I think if I looked at if I drew like the open loop Bode plot, it would look something like this, where this is 40 dB per decade right here. Okay? So, again, does this thing oscillate? And by the way, let's maybe actually, to help you guys out, so that's magnitude of H of S. Let's draw the phase of H of S over here. What does a phase plot look like?
Goes to minus 180.
Ah, okay, right. It looks something like that, right? Okay, so now I'm really asking the mathematical question here. Does this oscillate?
Mathematical?
Yeah.
No,
Okay, why not?
because you can only get minus 180.
Ah, there we go. Okay, so remember, in any two-pole system that looks like this, where I have two negative poles to begin with, or left half plane poles, I should say, technically, and I'll explain why this is obviously bogus in a second. Technically, remember, you always need, if you want to oscillate, you always need a gain of greater than 1 and a phase shift of minus 180 degrees, right? Well, if I really only have two poles, the maximum phase shift I can ever get is 180 degrees, right? So if I really, really had only two poles, this thing would not oscillate. Now, if you really built this circuit, would it oscillate or not?
Yeah.
Okay, of course, right? Why? What's missing from my silly model?
Parasitic capacitance.
Okay, some parasitic capacitors. I think, by the way, just by themselves, I can add all the caps I want over here, and I don't think I can quite get a minus 180 phase shift. But there's some other stuff there, too.
There's a feed forward 0.
Okay, there's a feed forward 0. You're actually right about that. I'm even going to ignore that. What else is there? Let me maybe ask it a different way. How many degrees of extra phase shift do you need in order to cause it to oscillate?
1.
Like 0, right? Delta extra phase shift causes it to oscillate. So if I just, I drew this wire right here. Let's say that was even 1 micron or even 0.1 micron or hell, I don't know, 10 nanometers long. Am I going to get some phase shift from that? Yeah, why?
CGS.
Don't even worry about CGS. I'm just, I'm using something even simpler. Can you get from point A to point B instantaneously?
No.
Yeah, you can't, right? There's speed of light and all this other Einstein and people like that who tell you all these problems about going from point A to point B, right? So point here is obviously in a real circuit. Just as an example, there's a tiny little bit of resistance there. Or there's just, time of flight to get from point A to point B. There's an extra, half of a degree of phase shift. So clearly, if you really did this, the thing would oscillate, right? So the only reason I mention this is just be careful whenever you use your sort of nice linear analogies, because there's usually lots of stuff that you're kind of ignoring and forgetting about that obviously would, let's say, qualitatively change the behavior of the circuit. Now, the good news is, even if this really didn't oscillate, somehow it was really only two poles, you probably wouldn't want to use this thing. right? You probably wouldn't want it just from a sort of settling standpoint. Why do I say that, by the way, just as a reminder? What would happen if you put like a step into the input? Even if it didn't exactly oscillate.
Take a long time to.
Yeah, it'll take forever to settle, right? Because even though it's not really oscillating, it'll do something like that, right? It'll just take really, really, really long time for it to ever actually settle to where you want it to go. Okay? So, let's actually take sort of a closer look at this thing. So, obviously, you're not really going to want to do this. You're going to want to try and build something that is indeed stable. So let's look at kind of actually the real Bode plot that we think we're going to get here. Okay? So let's say that I didn't actually place the two poles like right on top of each other, but let's say that they are close to each other. Okay? Which is actually, unless we really explicitly do something, is oftentimes going to be the case. So let's look at the magnitude of h of s right here. Of course, versus frequency. Okay, and so let's say that our Bode plot looks something like, and actually let me be more clear, this won't be h of s, let me call this magnitude of the t of s. So in other words, the open loop loop transfer. So let's say I have something that looks like this. So that's my P1, that's my P2. Okay? So, oh, and of course, let me draw the phase as well, because clearly that's important. So this is going to be the angle of T of S, also versus omega. Right? So, as we expect, that first pole, when it kicks in, right at the first pole, you get 45 degrees of phase shift. And then when that second pole kicks in, we're going to get another, essentially this whole range here, of course, is 90 degrees. That whole range is also 90 degrees. So at this point we have, let's say, minus 135 degrees. Okay? And of course, as we said a second ago, the asymptote is minus 180. Okay, so clearly the way I drew it now, if this was really my loop crossover, my unity gain frequency or the crossover of the open loop, ain't going to be stable, right? At least it's not going to have a very good phase margin, because I've already picked up quite a bit of phase shift by the time I get to this point. Okay, so now, without changing the amplifier, is there anything you can do to make this loop stable? Or is there some way you can sort of modify this whole loop transfer to make this thing stable?
Reduce the gain.
Okay, we can do some compensation. Let's, we'll talk about that more in a second. What'd you say, Brian?
Just reduce the gain.
Yeah, there we go. You just reduce the gain, right? Because, and I'll just draw this in a slightly different way than maybe you're used to, but if I just reduce the gain, that's kind of equivalent to just taking the x-axis. Oops, let me do that in a different color. That's kind of equivalent to just taking the x-axis and shifting it up, right? So indeed, if this was really my new loop transfer, and I shifted it up so that actually I crossed over right there, well, yeah, indeed. Now, I've only got, let's say, minus 90 degrees of phase shift. So the thing would indeed be stable, right? Okay, so now, why do I claim that this is actually, although you can do it, in general, is probably not the way you're going to want to make this thing work? What's the limitation here? Or to say it another way, what's the limitation here?
The range of gain that the amplifier can achieve.
Right. What's the limit on the amount of gain you can actually achieve?
The original gain divided by the DC gain
Original gain divided by the DC gain.
of T of S.
Yeah, so let me maybe ask it a slightly different way. In the limit, what's the maximum height right here that I'm allowed to use? And it actually doesn't depend on the original gain, because remember, the original gain, this point right here, is always just AV times P1, right?
Yeah.
And obviously, if I'm crossing over here, it's bad news, right? So, really, well, maybe ask the sort of sub-question to be clear. if I wanted to, let's say, have at least 45 degrees of phase margin, where would I have to put that blue line?
At P2.
Yeah, exactly. It had better touch P2, right? Okay, so now, if I have a first order system, meaning a single pole system, and I know that right here is where I'm going to hit that second pole. So let's say that these two are sort of reasonably far apart from each other, so we can use our nice, simple 20 dB per decade approximations. If I know that this point right here is 0 dB, what would be the linear gain at that point?
dB times P2 minus P1.
Ah, okay, so you actually did everything in the dB scale, which is, so I was just going to do it in linear, but basically that's P2 over P1, right? Which is equivalent to what you just said, right? Because if it's a first order roll-off, then as you go linearly up in frequency, the gain goes down linearly, right? So notice the maximum gain I can use and get 45 degrees of phase margin is just set by the spacing between those two poles, right? So now here's kind of the problem. If I said from the get-go that those two poles are close to each other, well, however close they are, that's the maximum open loop gain you can actually use. So let's say that I said that P2 over P1 was only a factor of 10. Why might that be bad from our standpoint? Why is it bad for us to have only closed loop gain of 10?
Accuracy.
Yeah, settling accuracy, right? If we wanted a settling accuracy of 10,000, then these two had better be spaced by more than 10,000, right? So, what this kind of says is that if we don't do something else, the maximum magnitude of T of S is limited by the spacing between the poles, okay? We generally don't want that. Okay, we generally want to be able to build our amplifier so that we can get really large gain, but still use multiple stages. And by the way, it may not be actually that easy to just sort of, without doing anything else, meaning just taking an amplifier like that and really spacing them by more than the factor of our open loop gain. So as people already talked about, and as hopefully you've seen many, many times before, obviously what you have to do is use some sort of compensation technique. Okay? Now, there's a whole long list of different compensation techniques that people have come up with over the years. I'm not going to sort of give you an exhaustive covering of all of them. So I'm going to assume that you've seen a lot of this stuff before. But what I want to do is just sort of look at a few general categories to kind of give us an idea of when might certain things apply and in what situations. Okay? So let's just start out with the first one, which is what I call narrow banding. Okay? So the idea here is actually quite simple. So what this basically says is, okay, this is really, by the way, kind of the brute force way of doing things. What this basically says is, let's say that this was my original magnitude of T of S, okay? And that it looked, let's say, something like that. So that's my P1, that's my P2. So the idea of narrow banding is just to say, okay, fine. Let me just somehow take one of the poles and make it much lower frequency, okay? Or somehow when I add my second stage, just make it really ridiculously slow, okay? So obviously what I'm doing when I do that is something like the following. So I'm just making it so my new thing looks something like this, okay? So obviously this is called narrow banding because all I did was I took whatever my P1 used to be and I just made it even slower, right? By however many orders of magnitude I needed to get the gain that I actually wanted to, okay? So from a stability standpoint, clearly this kind of works. But if I've done this, then it's also clear that I'm just making the darn thing slow, right? I've basically made the bandwidth slower than otherwise it could have been, right? So in general, that's usually not what you're going to want to do. However, there are actually some specific cases where something like this actually works sort of reasonably well, and in fact is probably even what you wanted to have happen. So let me just sort of draw an example of that. So let's say you have, some amplifier that you're trying to use, okay? But as we're going to see actually in a whole lot more detail in 1 second, a lot of times you really need to make sure that that amplifier has 0 offset in it, okay? Because sometimes you're just dealing with really, really small DC signals, and if there's any offset in the amplifier, you won't even see the signal you want to, okay? Well, so obviously if you want to somehow get rid of that offset, then what you could do is you can measure the output of the amplifier, right? And then basically try and grab only the DC portion and then feed it back to the input, right? So by the way, what this thing here is supposed to indicate is this is some sort of low-pass filter here, okay? So here, if really my only purpose is just to try and get rid of the DC offset of the amplifier, then it may not actually be so bad for me to use a very, very low bandwidth here, right? Because again, my only purpose of adding the second stage was to try and get a bunch of extra gain at DC to cancel the offset of this amplifier right here, okay? Does this kind of make sense to people, or? Now, by the way, here's the sort of interesting question related to this. Let's say that really, indeed, I'm building an amplifier that looks like this. This is, of course, V in, and that's V out. And again, I've added this really slow, sometimes people will call this a servo loop, by the way, because it's sort of servoing the input to get rid of whatever the DC offset is. Okay? So let's say I did indeed build something like this. If I was to plot the magnitude of V out over V in as a function of S, of course, versus omega, what would this transfer function look like? Okay, well, if I had a normal amplifier, let's say it looks something like that. Right? If I just had this amplifier by itself, then we could say that it looks something like this. Now, given that I've tied it into this feedback loop like this, what does it actually look like?
Band pass.
Yeah, it's going to be band pass, right? So what's actually going to look like is now, oops, like this, right? Why is it that it's band pass?
0.
Okay, yeah, I agree. There is a 0, but I guess maybe more physically what's going on there. What happens at low frequency?
The unity gain feedback, kind of.
Okay, in fact, actually, let's say this gain is big. Let's say that this gain in the amplifier at DC is, I don't know, 100. And let's say this one over here is 1,000. Is it actually unity gain feedback, or is it even worse than unity gain feedback? In terms of looking at that amplifier. Yeah, it's worse, right? In fact, it's actually, I don't even know what to call it. It's like gain of 1,000 feedback, right? And in fact, let's say that I really wanted my DC offset to be 0. How much gain would I put into this thing right here? If I truly wanted 0 offset.
Infinite.
Yeah, I'd put infinite gain right here, right? I'd make this an integrator. And then in fact, the DC gain of this whole thing would go to 0, right? Because guess what? You can't tell the difference between a DC input and a DC offset, which usually you'll model that as just something like this coming from the amplifier, okay? So again, we'll spend a whole lot more time talking about sort of similar things like this. And by the way, just in case it isn't clear, that point right there, if this has a certain pole, that point right there is always at that pole. Okay, and if it's not clear, you can work out the transfer function. You'll see that very, very quickly. Okay? But again, from a sort of higher level standpoint, from a compensation point of view, while you can do these kinds of things to kind of get things to work, most of the time, this isn't really what you want to do. Because you're really just sort of throwing away bandwidth in the feedback loop. And so maybe in something like offset cancellation, it's okay. But in general, this probably is not what you want. Okay? So we need to do something sort of, slightly more sophisticated. Well, so the other thing you can do, which is kind of, in almost some sense, the inverse of narrowbanding, is you can say, okay, well, if by adding another stage, I really can't make that stage so slow that it limits all of my whole bandwidth, why don't I instead just add another stage that's very fast? Okay? So as an example, people usually think of this as something like a pre-amplifier. So this kind of works. So again, the idea here is that, if before I had my single stage amplifier that looked like this, with a certain, let's say, P1, so now what I'm effectively doing is, if I want to add a preamp in front of it, by adding it, I just want to get a little bit of extra gain, but I want to make sure that whatever pole is introduced by that amplifier is at a high enough frequency that it won't bother me from the standpoint of closing the feedback loop. Okay? So again, this sort of works, but there's some limitations here. So in particular, notice I drew this as being resistively loaded. Well, I put a resistive load here because if I really want to get a very, very high frequency, that kind of means I can't have a very high output impedance here, right? If I really want to get a very fast response, I need a fairly low impedance on that amplifier. So what that typically means is, because I'm using a resistive load like this, that basically means I can't really give myself all that much more extra gain, right? I can maybe only get an extra gain of, I don't know, somewhere between 2 to maybe 10 if I'm really, really good. Which probably 10, by the way, is even too much. It's probably more like 2 to, I don't know, 4 or 5 at most. Okay? So again, this kind of works. But it's usually only if it's like, you just need that slight little extra bit of gain, right? You need like another 6 to 10 dB of gain to kind of push yourself over the edge and get the loop gain you want. So, by the way, I mentioned this as being a pre-amplifier. You can imagine you can also do it as a post-amplifier, but really kind of the same constraint holds, right? Because it's just, if you have to make that thing really fast, generally speaking, you can't actually get a whole lot of extra gain out of it, okay? So we've kind of knocked off the, sort of two simple, quote-unquote, things to do. So of course, as you guys, I think, should hopefully know very, very well from 140, the good news is there's something more clever that we can do that actually works pretty nicely, okay? And so the more clever thing that works pretty nicely is, of course, named after the guy who did it, and that's Miller compensation, okay? So the idea here is pretty simple. Let's just add in a capacitor, basically wrapped in negative feedback around that second stage, okay? And again, as I'm sure you guys know very, very well already, this kind of has this nice benefit of so-called pole splitting, okay? So maybe just as kind of review, what does that mean? What's really so magical and so great about Miller compensation? Why is it that we say all this pole splitting is so great from the standpoint of helping us out? What's sort of going on there?
You lower the frequency of your first pole and raise the frequency of the second pole.
Yeah, okay. So what this really means is you're essentially somehow taking that first pole and you're moving it to lower frequency. And that second pole, you're pushing it to higher frequency. In other words, you're increasing the separation of those two poles, right? That's definitely good news. By the way, physically, how is it that that's happening?
Miller effect.
Okay, well, yes, I know it's the Miller effect, but, what does that actually mean? Why is it, for example, that the first pole goes to a lower frequency?
Because you can model CC as C Miller, which is CC times the gain.
So I don't want any, if you use the word Miller, then, you've knocked out in terms of the explanation. So physically, what's happening? What does Miller effect actually mean? To be more specific, why is it that we say that when we talk about Miller effect, we say that that CC is effectively something like AV times CC? What's happening there?
Being bootstrapped.
Okay, that's actually kind of one way to think about it. So what do you mean by that? Maybe just to be specific, is it really that I have a capacitor that's AV times larger? Like, do I actually physically have a capacitor that's larger like that?
You magnify the voltage difference across the capacitor.
There we go. Right? So that's the whole trick. The trick here is that if I have something that's moving by, let's say, 1 millivolt over here, it's going to move by minus, let's say, I don't know, I'm making up the number, obviously, but 10 millivolts on the other side, right? So the voltage the capacitor sees is 1 plus AV times the input voltage, right? Why does seeing a larger voltage mean that it's sort of acting like a larger capacitance? Like physically, what's extra that you have to supply?
Charge.
Yeah, you got to supply extra charge, right? So for that same 1 millivolt to swing right here, you have to supply, in this case, 11 millivolts times C of charge out of this terminal right here. Okay? That's the whole deal with the Miller effect. It's just that actually the amount of charge you have to supply looking from that terminal has gone up by the gain. Okay? So that's one piece of the good news story. That's why the lower pole gets moved to a lower frequency, because we're effectively placing a larger capacitance onto this terminal here. Okay, now how about the other side of the story? Why did we say that the second pole actually moves out to a higher frequency? Say that again? Small output impedance. Okay, I agree with that, but physically, where does that small output impedance come from? You said something about 1 over GM. I agree with that too, but where is 1 over GM kind of coming to the picture here? At high frequencies, how can I redraw this circuit to kind of tell me effectively what it looks like?
A diode.
There we go. Right? At high frequencies, if I look at that second stage, I'll just draw that right here. Basically, that cap, right, just becomes a short. So guess what? Looks like I'm just driving a diode, right? So if I think about it, what I now have is I have my first stage driving a diode and then driving another cap, right? Well, the diode has an impedance of 1 over GM, which obviously is going to be much lower than, or really hopefully will be much lower than the output impedance of that current source, right? Which, if it is lower, is indeed why we're actually at high frequency. We're pushing out that second pole, right? Because rather than that second pole being set by the RO of this, it's going to be set by the 1 over GM from that diode, okay? So physically, that's why Miller compensation is kind of good news, okay? So now, this is hopefully going to be largely review, but maybe I'll sort of cast things into a slightly different form. Let's just walk through and sort of see what this implies about the overall stability of the structure. So just to make things clear, I'm going to redraw the actual amplifier we're talking about right here. Okay, so I've got my 2 stages, obviously. I've got my Miller cap right there. I've got some C2 right here. And then again, just like before, I'm going to pretend that there's some output resistance R1 right here, and some output resistance R2 right there, okay? Now let's just try and see if we can figure out what are the poles of this amplifier going to be, roughly speaking. So let's start out with the dominant pole. Roughly speaking, and I guess I should do this, where's that pole going to be? What's going to set that first pole? Open loop, by the way.
R1 times CC AV.
Okay, yeah, so to be completely correct, it's something like that, right? Now, by the way, if I was to sort of expand that out, what is that AV? In terms of small signal parameters. What is this AV right here?
R2.
Yeah, it's GM2 R2, right? So this is going to be minus 1 over R1 CC times 1 plus GM2 R2. Okay? So now I want to do a couple of things just to sort of make this a little bit more clear. So first, as Will at first said, let's assume GM2R2 is a big number. So I can kind of drop this 1 plus, okay? And then the other thing I want to do, again, just to make life sort of, or just make sort of physically things look a little bit more clear. Once I've dropped that 1 plus, I'm just going to multiply both the numerator and the denominator by GM1, okay? So I'm going to have R1 CC times GM2 R2. And then again, just because I'm somewhat arbitrarily going to multiply by GM1 on both the top and the bottom, I'm going to get this. Okay? So now, why did I do that? Well, notice, that's just the gain of the first stage. That's just the gain of the second stage, right? So that basically means that I can rewrite this whole thing as essentially being minus GM1 over AV of the whole amplifier times CC. Okay? So as you can imagine, I've written it this way because now if I close the thing into a feedback loop with some feedback factor, I can immediately figure out what is the closed loop gain going to be, or excuse me, the closed loop pole going to be, right? Because if I, for example, tied this thing into unity gain feedback, where would the closed loop pole be?
CC.
Yeah, just GM1 over CC, right? If I tied it into half gain feedback, meaning the feedback factor is a half, then it's just going to be GM1 over CC times a half, right? Okay, so that's good. We've got that out of the way. Now, let's see. So we got the first pole. Where do we think that second pole is roughly going to be at? What's going to set that?
GM2 over C2.
Yeah, there we go, right? So for that second pole, if we kind of look back at our picture right here, we're basically assuming that at high frequency, once that Miller capacitance kicks in, that second stage is just diode connected, right? So if it's diode connected, then the output impedance of the first stage should really just be 1 over GM2. And then the only cap we have really left is C2. Okay, so indeed, roughly speaking, that's going to be at minus GM2 over C2. Okay? Any questions on this, or? All right, so is that the end of the story, or do we have some more fun still in store for us here?
0.
Yeah, there's a 0. What kind of 0 do we have?
Feed forward 0.
Okay, it's a feed forward 0. I mean, like, which plane is it in? Left half plane, right half plane?
Right.
Yeah, it's right half plane. So now, physically, why? What does a right half plane 0 actually mean? Why is it that it's in the right half plane versus the left half plane?
Your feed forward will have the opposite sign as the final result.
Exactly, right? So remember, anytime you have right half plane zeros, what that usually means is that you had a stage whose gain used to be negative, and at high frequencies has become positive. Okay, and so just to be really clear, the reason that's happening here is just the following. At low frequency, if I just look at that second stage, right, the gain from there to there is negative. Because it's just, I move the voltage up, the transistor pulls a little bit more current out of here, and so obviously gain is negative, right? At high frequencies, the amplifier just looks like that, right? So obviously, if I move this input voltage, if I move that up, I just have a wire connecting the thing, right? Output's just going to move up, right? So clearly, I've got a right half plane 0, because again, the sign is flipping over. Okay, so keep that in mind, because we're going to see later sort of how we're going to make use of that. So now if you guys remember, there's sort of a simple way we can figure out what that right half plane 0 is. Turns out it's kind of identical to what we have done before, and hopefully you guys have seen this. So where is that right half plane 0 at? What frequency is that at? Anybody remember, or sort of remember the trick to figure it out?
Where the output equals
Ground
0.
output.
Yeah, so you basically ground the output, you put a little wiggle on the input, and then you just essentially write the loop equation, which in this case is going to turn out to be that, so I'll write it over here, that GMVI is equal to VI times SCC. Okay? So in other words, the feed forward 0 is just going to be at GM over CC. Okay? And again, this kind of intuitively makes sense because if you sort of think about it, that's the frequency at which the current that flows through that cap just directly is the same as the current coming out of the transistor. Okay? Yeah?
Is it GM1 or GM?
Oh, excuse me, GM2. There we go. It's GM2 over CC. Okay? Which again, hopefully intuitively should be clear just because we're talking about the second stage right here, right? Okay, so now here's another, let's say, we know where the pole is. Actually, we know where both poles are. We know where the right half plane 0 is. So now here's the sort of the interesting question. From the standpoint of stability, are right half plane poles good, bad, or ugly? What do you guys think?
Ugly.
Ugly. Why ugly? By the way, I agree. So, why is it ugly?
The phase shift goes down.
Okay, so it's ugly because you get negative phase shift. And what else?
Settling.
Sorry?
Settling.
Settling. I'm thinking from the standpoint of just, feedback loop stability right now. So we certainly get negative phase shift, but poles do that too, right? So what's particularly nasty about right half plane zeros in terms of stability?
It upped the gain. So
Yeah, there we go, right? Not only do you get negative phase shift, it also increases the gain, right? So if we just think about those Bode plots we were drawing before, right around the crossover, if you have a right half plane 0, not only will the gain start flattening out, the phase will also start going negative. In other words, it's much harder for you to cross with gain less than 1 once you've done that. Okay? So I indeed agree. Right half plane zeros are ugly. Okay? And we're going to see in 1 second just how sort of ugly they are in terms of setting whether or not we really get to do what we want to do. Okay? So now that we know those sort of poles and that 0, now we can actually sort of take a look at what does this imply from the standpoint of us doing some, let's say, phase margin engineering. Okay? In other words, taking that amplifier and tying it into a feedback loop. Okay, well, so as we kind of talked about before, anytime you take an amplifier and you want to know if it's stable, you have to know what's the feedback that you're applying to it. Okay, so unfortunately, if you're like somebody building an amplifier for, let's say, DigiKey or something like that, like a general purpose kind of thing, you unfortunately don't necessarily know how your amplifier is going to be used, right? So in those cases, a lot of times, and in fact, probably even in 140, a lot of times you were told, okay, make your amplifier unity gain stable. Or in fact, maybe even make it, somebody could be really mean to you and actually even add gain in the feedback loop, right? So maybe you're even more paranoid than that. Well, as we're going to see in 1 second, if you always make your thing basically, let's say, unity gain or stable under the absolute worst case, you're always going to have to pay something for it. Usually you're going to have to pay power or speed or something along those lines. So in our context, or I should say usually in integrated circuits, a lot of times you actually know how your amplifier is going to be used. And so as we'll see in 1 second, it actually pays off quite a bit for you to not make it stable under the absolute worst possible case that anyone could ever possibly use the thing, but only make it stable under the way you are using the design. Okay? So in order to see that, let's just sort of, again, quickly figure out what some of the sort of closed loop poles and zeros and how that's going to affect everything. Okay? So first, as we had said a second ago, once I close the thing into a feedback loop, and I want to know where's the unity gain frequency or where's the crossover frequency, that's really just going to be at F times GM1 over CC. Right? And again, that's just coming about from the pole having been at GM1 over AV0 times CC. Okay? So that's where my unity gain frequency is going to be. So now, just like we had sort of talked about in the context of settling, we know that if we want to get a certain settling behavior, we should put our non-dominant pole at some factor k away from that unity gain frequency. So as an example, we said that if we wanted, the best settling for something like a 0.1% relative error, we would make this k something like 3.3. Okay? So now what I want to do is just taking this constraint right here, that I want to place that non-dominant pole at k times the unity gain frequency. I just want to use this to come up with essentially what's the constraint on my Miller compensation capacitor size. Okay? And so to do that, I'm just going to rewrite this thing. So remember, P2 is just at GM2 over, C2. Okay? And of course, K times omega U, if we just plug that in, that's just K times F times GM1 over CC. Okay, so if you just rearrange this thing slightly, what you very quickly will see is that it basically tells you that your compensation capacitor has to be greater than K times the feedback factor F times C2 times GM1 over GM2. Okay? Say that again? Okay, so there's kind of a couple of things we should sort of notice here, right? So first of all, the farther away you want that non-dominant pole to be from your crossover, the larger you're going to have to make CC. Right? In other words, the bigger the K is, the larger you're going to have to make CC. In fact, the larger the feedback factor is, meaning the closer to unity gain or even beyond unity gain you get, again, the larger you have to make CC. Because it's that CC that's separating those two poles away from each other. Not only that, in fact, if I actually was to somehow have to drive larger load capacitance, meaning if I increase C2, again, I'm going to have to increase CC, right? That compensation cap. That's actually quite different than if you think about like your normal single stage or single pole amplifiers. Usually the more cap you put at the output, kind of the better things look, right? The more dominant you can say that pole is. Well, now with a Miller compensated, more cap you put at the output, the worse your stability actually gets. Okay? So again, if you kind of look at this, this is all telling you why is it that if you don't have to sort of engineer the thing to have the absolute worst feedback factor, actually you can save quite a bit of compensation cap. And as we'll see, because actually given that our bandwidth is set by that compensation cap, you can actually save quite a bit of power as well. Okay? Now, so far, this was all just based on that non-dominant pole. As we said before, we really have to worry about that 0 also. Well, unfortunately, if I look at where is that 0 relative to my unity gain frequency, and remember, I really want to push that 0 as far away as I can in order to make sure it doesn't screw me up, that's actually set only by this. Okay? In other words, the only thing that changes where's the 0 relative to my crossover is the feedback factor, which generally speaking I can't do anything about because that's how I was trying to build my circuit anyways, and GM2 over GM1. Okay? So this I can't change. This is really the only thing I have left for me. But actually I'm going to claim that even though I could change GM2 over GM1, in general, this is probably not going to be a very favorable thing to do. In other words, I'm not really going to be able to make this GM2 a whole lot larger than GM1. So why do I say that? What knobs do I have available to turn to actually change GM2 and GM1?
Width.
Okay, width, and what else?
Current.
Bias current, right? Okay, so if I really, so width, okay, really width, what you kind of mean is actually V star, right? Okay, so maybe I can actually build things with like, okay, maybe the first stage has a large V star, and the second stage has a small V star, but I can maybe only get a factor of 2 out of that, right? So if I really want to get bigger GM in the second stage, that basically means I have to spend some power. So now, why do I claim that I probably don't want to do that? Other than just in general, I don't like spending power. What kind of sucks about putting a bunch of extra current into the second stage?
You increase P2.
Okay, maybe. I mean, but let me ask it maybe a different way. Does that extra power that I put in that second stage, does it make me settle any faster? What do you guys think? Does it help my settling at all? I'll give you a hint. Does that depend on GM2?
No.
No, right? So I can put as much power as I want in that second stage. Doesn't do me squat from the standpoint of actually settling. And remember, the whole reason you should be burning power in the first place is to settle stuff. Because otherwise, there's no reason you need to intrinsically be burning power, right? So what this basically says is this, even though there's this knob here, really, I'm not free to turn it that much. Because if I turn it, I'm essentially just going to be wasting power and not actually really intrinsically adding to my performance. Now, granted, I need to make sure the thing is stable, so clearly, if you have to do it, you have to do it. But you'd really like to have another way of doing things, right? You'd really like to be able to actually not have to worry about this right half plane 0. Because the solution is painful. At least this way, I mean. Okay, well, so again, as I assume you guys have heard from 140, what can I do to actually get around this problem? What's an additional trick I can play in my compensation network? Which, if you're flipping the slide, you should know already the answer to as well. Yeah, I have to add a resistor, right? I have to add what's called a nulling resistor. So, of course, the way that looks is something like this. Okay, so I have my first stage, I have my second stage, but now instead of just having a compensation cap, I'm actually going to put some resistor right here. Okay, and so of course I still have my C2 right here. Okay, so now, since you guys knew what the nulling resistor is, now I'll ask you the more fun question, or the more interesting question. Why is it that that nulling resistor helps? Or in particular, how can I use that nulling resistor to actually completely get rid of the right half plane 0? Any thoughts? And again, of course, I want the intuitive answer, no math. Because yes, I'm sure that you can look at this equation and tell me what the math is saying, but that's not particularly useful.
At high frequency, although CC short, you still have R2, so there's still some gain.
Ah, okay, what kind of gain?
Negative.
There we go. That's exactly it, right? So the whole trick with that nulling resistor is that now, at high frequencies, just like you said, even though the capacitor is a short, as long as this resistor is large enough, then actually my gain from this point to this point could still be negative, right? Because what this resistor is really doing is it's limiting the amount of current that flows directly from the input to the output. And therefore, it's limiting the amount of the sort of wrong sign of the gain, right? So in fact, as you should already know, as you can probably just figure out even by looking at something like this, if you wanted to know exactly what was the point at which you basically didn't have any feed-forward 0 at all, well, basically what that's saying is that you want to make it so that this current flowing through here is the same as the current flowing through the transistor, right? That means that at that point, if those two are just canceling each other, then it's kind of like there's no feed forward at all, right? In other words, the 0 has completely gone away. Well, just like we had done before, that basically tells you that the GM of the transistor, and actually I'll be sort of more clear, the GM times V in would of course be equal to V in over RZ. In other words, that RZ is just equal to 1 over GM of that second stage. Okay? So by the way, for those of you guys who like sort of poles and zeros, if you meet this particular condition here, meaning that there's no feed forward at all, meaning there's no 0, that effectively means you've pushed the 0 out to infinite frequency. Okay? If it's out at infinite frequency, it basically has no effect on your dynamics. Now, there is one piece of bad news here, which is even though I can sort of get rid of that right half plane 0, or at least push it out to really, really high frequencies, I've now actually added an extra pole, right? Because this resistor here is sort of decoupling between these two sides. So now I'm actually going to have a third pole. That third pole is going to sit at this 1 over RZ times C1, okay? So you have to be a little bit careful because since you've added that extra pole in, it may actually come in and add in a little bit of extra negative phase shift. But as long as you're not too aggressive and you don't actually try and make this RZ too big, then usually you're sort of okay with that. Now, again, there's some really aggressive things that people sometimes talk about doing, like turns out if you make this RZ even larger than 1 over GM, you can actually have the pole come back into the left half plane. It actually becomes like a feed forward in the good way, 0. And you can actually even try and have it cancel this pole. Long story short, don't do it, because if you over-cancel it, you'll run into problems. Okay, so just basically, you should try and push this out to really high frequencies, and once it's there, most likely you won't have to worry too much about it anymore. Okay? But there is, of course, just one thing we have to be a little bit careful about. So let's think about how we'd actually build this thing. So again, I'll just sort of redraw our amplifier. So I've got, of course, my first stage. I've got my second stage. And let's say I build the thing like that. And so let's say I build this thing out of a polysilicon resistor. Okay? So I'm sure I can build it. I can tweak the thing. It'll work great in Spice. Why might I not exactly want to do things that way? What's the problem with building it like that? What do you guys think? I have one person who has the evil smile, so it sounds like they have the right idea, but maybe somebody else. So what would happen if I actually built this thing out of a polysilicon resistor? What might you worry about? I'll give you guys a quick hint here. And yes, fortunately, I only had one thing that was boxed right there. So where do you want to set that resistor to be? What value do we want to choose for it?
1 over GM2.
1 over GM2. Yeah, I agree with that. Okay, so what's the problem with building it out of a piece of polysilicon, just a strip of polysilicon, basically?
How much area?
It's not
Too
gonna
much
match.
area. Maybe not.
It's not gonna match the GM.
Ah, there we go, right? Remember, if you want your R to somehow be equal to 1 over GM, if I just, I trust you can do this in Spice beautifully well, but as soon as you fabricate the chip, you're going to get 10 chips back, and every single one of them will have a different relationship between R and 1 over GM. Because the sheet resistance of the poly has absolutely nothing to do with what's the 1 over GM that you've gotten, right? Because if the oxide thickness changes, or the mobility changes, or God knows what changes, no reason why that has any correlation whatsoever with this resistance. Okay? So just quickly, if you were to actually build this thing, let's say, we just said there's a certain reason why we don't want to build this as a piece of polysilicon. How do you think you might want to build it?
Transistor.
Okay, yeah, you probably want to use a transistor, right? In fact, you probably want to use, in particular, an NMOS transistor. So here, you're probably actually going to bias this thing in the triode region. So that means there's going to be some sort of magic V gate right there. Because at least if you use a transistor, at least somehow if you came up with a really nice special V gate, then the resistance of that transistor should roughly track with the GM of your actual circuit that you care about. Now, again, I'm not actually going to spend a lot of time on it because there's lots of other sort of books and things you can take a look at. So there are ways you can come up with VGs that, roughly speaking, will track. But they're a little bit complicated and they may not actually work all that well once you have short channel devices. So a lot of the times what people will actually do is they say, well, okay, screw it. I'm lazy. I'm just going to tie this to VDD. Okay? obviously doesn't work perfectly, but kind of works halfway okay. You just have to be a little bit careful because, again, you don't necessarily know where these voltages are going to be. And so if it's up at a reasonably high voltage, the VGS on the transistor may not be that great. So sometimes you may even do something like that. In other words, add in the PMOS transistor in parallel and tie its gate to ground. Now again, that's not to say that this is the most robust way of doing it, but at least there's some correlation between how this resistance varies and how the GM of the transistors inside of your amplifier are varying. Does this make sense to everybody? Or? Okay, so we'll pick back up with this on Tuesday, so I'll see you guys all then.